Okay, thank you very much. I actually wanted to give a talk like Rahul, but I was told I should talk about research and just have one slide about the, what we should do. So I'm going to talk about video object segmentation and action detection or segmentation. These are two related problems, and from my point of view, if we can solve that problem, then we can do lots of things. So just as you saw, that the video object segmentation is given a video like this. We want to segment the primary object from that automatically. And the action detection, given a video like this, we want to put a bounding box where the action is happening and also what is the action. So then the ultimate, what we want to do is a segmentation. Pixel-wise segmentation is compared putting a window, which is a very precise, fine contour, which will give you. So all these problems are related, and that's the kind of ultimate goal of video understanding. So I'm going to go through several things we have been doing to solve that problem and kind of relate them. So this is the paper we had in NIPS last year, and we have been looking into this capsule network, which is beyond the CNN, with the recent work from Hinton. So the idea is that it capsule order add an extra structure to the model entities. It's a group of neurons, and then there's a routing by agreement where we have part the whole relationship, and it's inspired from inverse graphics. Okay, so the capsule is modeled by a pose matrix, which is a 4x4 matrix, and the activation, and then the capsule in the lower level actually vote for the capsule at a higher level, and the votes are given by the pose M multiplied by a transformation matrix, and you get a vote. And then these votes are the prediction of the whole, and then we have the agreement, routing by agreement for the grouping of the votes. So now capsule networks have been demonstrated on small images like MNIST, but there was a problem when you work in the high dimensional data or video. Then there was a problem, and we have kind of addressed this problem, and we have been successful to use the capsule for the video. And the reason they have been hard because computationally they're very expensive and they require a lot of memory. So it's very hard to fit in capsule in the one GPU. So what we did is that we use the same transformation matrix in a local receptive field that reduces a lot of computation, and also we do the capsule pooling, and that helps also. So now for this problem of segmenting or detecting the action from a video, so we have an input clip of 8 frames, and then we want to get an output clip, put a window, the pixel-wise segmentation, and determine what is the action being performed. So we have, this is the network, and so we have the encoder, and in that we have the initially several layers, 3D convolution, and then we have from the 2 capsule layer, and this routing is done from one capsule layer to other capsule layer, and then we have at the end the fully connected capsule layer, which depends on how many classes we have. Okay, and the capsule which has the highest activation is actually action, which we want to detect. So this is a decoder which will take these capsules from the fully connected, and then we will have the skip connection, and we will kind of upscale this, and we will come up with the video. So we get pretty good results. This is the cricket bowling, this is biking, this is driving, and gymnastic, and quantitative results actually are much better. So this was the results on the UCF Sports. UCF Sports is a very small data set, not many samples, so it was about 1% difference. But we're very happy to see we have about 15% improvement in JHMDB, and amazingly 20% improvement in the UCF 10124. So this was about using the capsule network to detect the actions. And then we actually use the same idea of capsule network for video object segmentation. This is a paper we'll present in ICCV next month. So the idea here, the problem is, this is actually a very interesting problem and very nice data set, and there's a context also in ICCV. There's a data set called YouTube VOS. And the idea is that we are given the first frame, segmentation in a video, and we want to actually, given this segmentation and video, we want to segment that particular object. Okay? So again, here we use capsules, and so we have the capsules for the video, and we have a capsule for the video frame, single frame, and the capsules in the video are all objects in a video, and the capsule in the single frame are the object of interest, and we combine these and get agreement and do the routing, and we can solve this problem. So this architecture, so we have video encoder. Again, we get the features from standard convolution, and then we have a decoder which has the capsule coming from the single segmented frame, and we have memory module, and then we have these combining of these two capsules from the single frame, first frame, and also the video. And then finally, we can do the decoding and get the segmentation. And we get very good results. These are the typical results for the single objects, and very nice pixel-wise segmentation. And these are for the multiple objects. You can do, say several airplanes and several sheep. And this also works for the occlusion. So if this is behind the trees, then we are able to recover that. So another example, if it's behind the car, the bus, then we can still segment that. And this also works for the very small objects, which is very nice results here. And there's some more examples here, and so on. So the results wise, we do close to the state of art, and I think better in couple of measure and very close in other measure, but we have very fast implementation. So we can do about 13 frames per second segmentation for this, and this is kind of shows the frame per second and the performance. So we are a little lower than this one, but we are 100 times faster than that, which is pretty good, and particular using capsules, because that's known to be computationally very expensive in memory. So this is about the using capsules to do video object segmentation. And now the question is that can we do this segmentation using a sentence instead of the first segmented frame? So that's another problem. Again, we use the capsules here, and so idea here is that we are given a video, and like this. So that she's the one. Okay, so then we are given a sentence like this, like a dog that is walking around the red cones. So we want to segment that person, and here we have the woman in green top standing on the left. We want to segment that. So that's a very nice way to use the language in the video. So out of the way so that he knows she's the one in charge. Okay. So again, here we have the two sets of capsules, and we combine these capsules. In the previous one, we have capsule from the single frame, the initial frame, and capsule from video. Here we have capsule from the text, and the same idea, we can do this. And so we have a given video, we do the encoding, and do the capsule from here, and we have a sentence, we do the word to vec and get the encoding of that, and then we combine them, multi-modal routing, and these get the capsules, and then we do the decoder to get the segmentation. Okay, so these are the qualitative results. So first is the person is walking backwards while being followed by a dog, and this is segmentation, and then a black dog is crawling, and which is shown in the yellow. So it's very nice segmentation. This is another example. We have three things here. Baby crawling in a corridor, which is shown in the green, and the dog on the right is crawling, which is shown in the yellow, and then we have dog on the left crawling, which is shown in the blue. So which is also nice. So these are the videos. So that's a ground truth, and this is based on a keyframe, and this is the based on the bounding boxes in all the frames. Another example here, baby in the white is climbing the stairs, and then this has baby sitting on to the ground, which is shown in the green, and the pink ball rolling. And this one is the example of Kate bouncing up and down, and then guy in white shirt and kept filming car from the left side. So this is the A to D data set from Jason Corso, and I think these sentences were generated by Case. So performance-wise, we do pretty well in all these metrics. There are few of these approaches we have very good results here. So this was about using Capsule to solve the video segmentation using a sentence. And so let me conclude with this paper we presented a couple of weeks ago here in BMVC, where we want to actually solve these both problems, these video segmentation and also action detection. And the good thing about this is that we are using this 3D separable convolution, and that reduces the operation significantly, and also the memory, and the performance is very close to the base performance here. So which is nice. So these are the results on the action segmentation and classification. So as you see that we not only have the class label, but we have a segmentation, and we don't have a background. So we have very nice contour segmentation. So segmentation is much more interesting and important as compared to bounding boxes, because that includes also background. And the numbers are also pretty good on the on this data set. So so thank you about this, and then let me spend a couple of minutes about what is missing in video understanding. So one is, I think we have made a lot of progress, so I'm pretty optimistic, happy about that. And the reason is that if you look at UCF 101, we started this data set in 2012, and now it's done. I mean, we have 100%, So this problem is solved for 101 classes, and that time was the largest data set, and there's a huge improvement. And mainly the deep learning and also mainly the Connect 600, 700 that helps to get the better features. And same progress has been made also on the detection. As you see here, that action detection also we have made improvement. Still there's a gap. In this one, we have, even though UCF 101, but it is only 24 classes. So that's one thing we want to discuss tomorrow. That'll be very nice if we can have the annotation for the rest of the classes, because there are lots of classes we don't have annotations. So from my point of view, as Rahul mentioned, the video is more complex. We have the time dimension, so it's X, Y, and T, and it also have motion. And so, the standard methods, we look at appearance in the image and so on, but there is no direct way to compute the motion. Of course, you can compute optical flow, but that, if you want to use just 3D convolution, motion is implicit, and that is, I think, important point to notice. Actually, in the CVPR, there was a couple of interesting papers where they are actually doing the motion and putting an embedding. So other thing is that the annotations are hard, because you can annotate very easily images, say there's object, but there are thousands of frames, and you want to put a bounding boson on each frame, and that's very difficult. And of course, it requires more memory. Instead of one frame, you have so many frames. And GPU power, you cannot, it's very difficult to fit a GPU, one thing in one GPU, and especially for universities. I mean, you can do DVD gain for the, UCF 101 and our Connectix in DeepMind, but we cannot do that in UCF because we don't have the resources. You can use TPU and so on. So also, as was mentioned, that we have to look into different definitions of these video, the actions, the movement actions, complex actions, much more harder. And so also there are very few people working in video as compared to images. So we need to increase this community, then we will have more power to solve this problem. Thank you.